G'day ladies and gentlemen, it is the Raging Ranga here, and welcome back to our topic on derivatives. This time we're looking at increasing and decreasing functions. So what this section is going to do is it's going to prepare you for the next section, which will be kind of to do with optimization. But we need to know when something's about to be optimized. How can we tell when our graph here is about to be optimized or is coming up to a point of interest? Because there are a few points of interest, particularly these points here, and we'll explain why they're points of interest in the next few videos. But first of all, it can be useful to know what a function is doing between some given intervals. So what's it doing in here? Or what's it doing in here? Or what's it doing after this point, going on to infinity and beyond? Yeah, some good relevant humor there. All right, so we commonly use the algebraic notation shown in the table to describe subsets of real numbers corresponding to intervals. So again, this is a bit of a rehash of a topic we did earlier on interval notation. So intervals being when your x value is either greater or less than or between a certain set of values. You've got a range set for your x values and you're interested in what it's doing in that set. If you haven't watched that video there, pause this one, go and watch it, and like, rate, subscribe, all that kind of stuff for it. Anyway, back onto here. So for example, the sign there means that x is greater than or equal to. Remember, the crocodile always wants to eat the bigger number. Nom, 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 nom. So, in this case, this means x is greater than or equal to 2. It could also be written as 2 is less than or equal to x, but typically, with most things, we like to keep the x on the left-hand side. For example, when we're doing algebraic equations, we like to end up with x on the left rather than on the right. That's why we have it there. And then in geometric form, you're going to end up with this here. We've got our one-dimensional number line for x. There's 2, and x is the red arrow, everything greater than 2. But we also colour in the dot on 2 to imply that it includes 2, the actual number 2, the integer 2. If, on the other hand, we had x was greater than 2, it'll look exactly the same on the number line, except the dot isn't coloured in. So x is everything greater than 2, just not 2. X could be 2.0000000, for 100,000 zeros, 1, but it still can't be 2. It can't be exactly the integer 2. Why that's important, I don't know. You'll have to go to uni for that one. I'm just a teacher. So, when we then have x being less than something, we use this notation here. So x is less than or equal to 4. Crocodile wants to eat the bigger number, so it's facing the bigger number. X is less than it. And arrow goes to the left instead. Again, colour in the dot for included. Same goes here for less than, rather than less than or equal to. And then down here, this is when x is between two set values. So in these ones here, there is no, well, first of all, in these ones here, there's no upper bound to x. X can go on to infinity. In these here, there's no lower bound, so x can go on to negative infinity. But in these ones here, x has a lower and upper bound. So it has a start and a finish. So for example here, 2 is less than or equal to x, which is less than or equal to 4. So 2 represents the lower bound there. Again, colour in the dot to represent that x can equal to. The red bar is all the values x can be, and then it's capped off by 4. Notice that x can also equal 4, so the dot's coloured in. Here, slightly different notation. X is still bounded by 2 and 4, but in this case, x cannot be 4 because x is less than 4. So again, that's just your interval notation, and this is now going to start to apply to functions and to derivatives. Yay! Yay! So, suppose S is the interval in the domain of f of x, so that f of x is defined for all x in S. So S will be all the f of x values, so as in the y values, that satisfy the domain. So for example, if that was our graph there, and let's say we're talking about all the values of x from A all the way up to B, well then the domain, remember the domain are all the the interval, so the domain is everything between A and B. Remember, domain is on your x-axis. So S is an interval in the domain such that x is defined within that interval. So S will be every set of values between A and B. So what we can say is that f of x, so the graph f of x here, which we've got, so let's get rid of some of this stuff here so you can see it clearly. I can see clearly now, the pen has gone. Alright, so f of x is increasing within this domain S if fa is less than fb. So let's mark in those points. There's fa, and there's fb. And if you're doing this course, hopefully you're learning more than fa. Don't tell your parents I said that. So there's fa. It is less than fb, or less than or equal to fb. So we can say that in this interval here, f of x is increasing. So in this domain here, in this interval, we can say that the graph of f of x is increasing, which kind of makes sense. It's going upwards. But this is just the mathematical way of saying it. And all A and B are in S, so all the values in there have to satisfy that, where A is less than B. So again, if I had a graph that looked a bit like that, there's A, there's B, we cannot say that this graph is strictly increasing in this domain, because here's A, and if I picked that as A, and I picked another B, say down here, then this A is smaller than B on the x-axis, but FA is bigger than FB in this particular spot, so it is not strictly increasing in that region. So in that interval, I should say. We are only interested in cases where for the entire region, it's going up, is the simple way of saying that. So we can say that f of x is increasing in this interval S when it's always going upwards, or it's not going downwards. So it might plateau for a bit, go flat for a bit, but then as long as it's increasing, that's the main thing. On the other hand, if it's decreasing, so let's say we had, let's say we had A there and B there. Well, what you can see now is there's our f of A, there's our f of B, and it is now decreasing. So this interval here is decreasing in the interval S. So I should say the function is decreasing in this interval S. because FA is greater than or equal to FB when A and B are contained within this region in here, contained with this interval here, and A is less than B. A is less than B. So I could pick any points within this region, and FA will always be bigger than FB. So the simplified way of saying that is that as long as the graph is always going downwards or not going upwards, so it might flatten out for a bit, then we say that the graph is decreasing in that interval. Okay, so take a minute to rewatch that if that didn't make sense, and let's have a look here at another example. What about the point where x equals 0? So here's y equals x squared, and it is decreasing for x is less than or equal to 0. So because remember, this goes on forever to negative infinity. Well, this goes on forever to negative infinity. So we can say that for x is everything up to and including 0 on the left-hand side, so x is less than or equal to 0, it is decreasing. The graph is going downwards. Remember, we go from left to right. So everywhere from the left, we're going down. And we also include 0. So at 0, you can see it's actually a flat spot. It's a horizontal gradient. But we can say that it's decreasing at that point as well. We can say that it's increasing for x is greater than or equal to 0. So going up that way, you can see it's increasing. It's getting bigger and bigger and bigger, and that will go on to a positive infinity. There's no right bound on that. And it also includes 0 there. So people often get confused about that point x equals 0. Raging Ranga. It doesn't make sense that it'd be increasing in that point there, or decreasing because it's going flat. So how can it be increasing and decreasing at the same point? Well, the reality is that it's kind of contextual. If we're defining a certain point which has gone flat, we can consider it either decreasing for an interval that's decreasing or increasing for an interval that is increasing. So it's contextual. You can apply it to either one, but that only works when you have a flat spot, so a horizontal point on your graph. You can apply it to either the decreasing interval or the increasing interval. You don't disclude it. So it's not x is less than 0, x is greater than 0. You include it in both or either one according to what you're interested in. So, example here. Let's find the intervals where f of x is increasing and decreasing. Well, hopefully it shouldn't be too tricky to see. Let's start with all the increasing bits. Well, we're not just looking between these points, we're looking everywhere on this graph. So here's our first section of increasing. Remember, we start from the left and work to the right. So, first section of increasing is right here. Don't be confused by this little arrowhead. It does not mean the graph is going that way. It just means it goes on forever downwards. So think of it like a dot, dot, dot. So then, this all the way up to x equals -1 is increasing. This is decreasing, so we'll leave that out for now. And then this section here, going on to infinity, that's increasing as well. So we've got two increasing intervals, which is x is less than or equal to -1. Again, we can include -1 here because it's a horizontal slope point, which we can include. And also x is greater than or equal to 2. Again, we can include x equals 2 there, and then everything greater than or equal to that. On the other hand, our decreasing section has a lower and upper bound. There's only one decreasing section, and it has a lower and upper bound. So the lower bound is -1. The upper bound is 2. Again, the whole thing is that we're looking at the points on the x-axis. So there's -1, which is the lower bound, and there's 2, which is the upper bound. Even though this point is higher than this point in terms of x, this is the lower bound, and this is the upper bound. So when you've got the lower bound and upper bound, you can plug it in here. F of x, so our graph is decreasing for -1 is less than or equal to x, less than or equal to 2. So there's our lower bound, there's our upper bound, and we can include those as well. That looks a bit like 3x squared plus 6x. Looks a bit like that there. So our key points, they're at 0 and there at 2. Of course, you can find what those points are if you need to using GSolve and to find the xcalc when y equals 0. And you can get the point there and there. So those are your key points, 0 and 2. So let's have a look. Everywhere to the left, it is negative. Our derivative graph is negative. So you put in the negative sign. Everywhere to the in between 0 and 2 is positive. So we put in the positive sign there. And then everywhere greater than 2 or equal to 2 is negative. So we put in the negative sign there. So we can say that f of x is decreasing for x is less than or equal to 0, x is greater than or equal to 2, and increasing in this set interval here, 0 is less than or equal to x, which is less than or equal to 2. You can apply exactly the same thing to part B. I'm not going to go through this in minute detail because you can give this a go yourself. Draw the graph of your derivative. So first of all, first step, find the derivative. First step, find the derivative. Second step, graph it. Graph the derivative. And then third step, mark on your sign diagram. And you're good to go. Well, ladies and gentlemen, that is it for this video. So, until next time, stay classy.